investigate acid-base buffers. But firstly, what does a buffer do? The buffer solution can reduce the change in pH with the addition of small amounts of an acid or a base to the buffer. It reduces the shift in equilibrium with the addition of hydrogen ions or hydroxide ions. So, the buffer summary: it resists a change in pH. When small amounts of acid or alkali are added, the pH changes little compared to an unbuffered solution. It's a solution of a weak acid and a salt of that weak acid. And you can scan that to see some worked calculations. So why do they work? So weak acid, look at the first equation. The forward arrow is very small. The weak acid is only partially dissociated into ions. And it's a reversible reaction, so it's going to have an equilibrium constant K. Because it's acid dissociation, it's K subscript A. And we can write out the value in terms of the concentration in moles per decimeter cube. Only works for weak acids because they form an equilibrium of the undissociated acid and some dissociation. And if you add one or more of the ions, you're going to alter the equilibrium position, and a reminder of Le Chatelier's principle. And so we've got Ka, and we're going to rearrange that equation so that the H plus ion here with water, H3O plus ion, is written in terms of Ka, the concentration of the undissociated acid, and the concentration of the acetate ion. Multiply both sides by -1 and log both sides. And as you do that, you get the equation that's given here. And log 10 of H3O plus is your pH. And log 10 of your Ka is your pKa. And if you flip the acetic acid concentration and the ethanoate concentration, if you flip it, you have to change the sign with the log. And at the bottom there, that is your Henderson-Hasselbalch equation. And we can call it the bottom conjugate base over the weak acid. So salt over the weak acid concentration. So we're going to make a buffer and investigate how it changes when small amounts of the following solutions there, the HCl and NaOH, are added. And so here's what you will need: burettes, one with the hydrochloric acid, one with the sodium hydroxide solution, pH 7 buffer, and your potassium hydrogen phthalate, and it says 2 slides further on, and some boiled distilled water just to reduce the amount of dissolved CO2, but it has to have been cooled down. And there is the solution again of what you need. And pause this to see the details exactly. So about 2 grams of potassium hydrogen phthalate, but know the exact mass to 3 significant figures and dissolve it in the boiled distilled water and make it up to 100 centimeter cubed, so you can calculate the exact molarity. And you transfer this to an erlenmeyer flask, and you add some boiled distilled water and call it solution A. And to a second solution, what you're going to do here is add 25 centimetre cubed of potassium hydrogen phthalate and 25 centimetre cubed of sodium hydroxide. And that would then end up as 0.05 of your phthalate ions of your salt. And here, with the next steps, what you're going to add, I'm not going to go through all of them, but we're going to look down the line headed first activity. So with a 10 centimetre cube pipette, these are accurate measurements, you're going to get 10 centimetre cubed of 0.1 molar HCl, add 10 centimetre cubed of distilled water, measure its pH, add 0.1 molar solution of sodium hydroxide from the burette and measure its pH. Repeat that, adding another centimetre cubed of sodium hydroxide and measure its pH. And then keep doing that, each time measuring the pH and swirling until you've added 15 centimetre cubed. So record the amount of sodium hydroxide added and the pH each time. And you've got a second activity and a third activity with the buffered solution. And here you have looking at what you're going to do with the sodium hydroxide, which is really item 3 from the previous one. And then the next one, solutions to add number 2, this is adding 0.1 molar HCl and telling you the procedure for that. So pause as you're doing that one. So each time record the volume of potassium hydrogen phthalate and the other amounts. Record your burette readings, initial, final, and subtract the two to get the actual measurement. Record your pH measurements for each solution, so label what you're doing each time. And then you're going to draw graphs of pH against concentration added of the material for each part of the lab. So, a little bit of a review. The buffer resists a change in pH. When small amount of acid is added, the pH will change little compared to an unbuffered solution. And the buffer is a weak acid with the salt of the weak acid present. And a little summary of how to make them. Number 1, in fact, in all of them, you start off with 50 centimetre cubed of your weak acid, 0.1 molar ethanoic acid. And to the first one, you're not adding anything, so it is just a weak acid. In the second one, you're going to add 25 centimetre cubed of 0.1 molar sodium hydroxide to the 50 centimetre cubed of 0.1 molar ethanoic acid. That's your buffer solution. You've still got some unreacted weak acid and you've got your salt, your sodium ethanoate. The third one, if you add 50 centimetre cubed, and it's not purple by the way, it's just so you can see it better, 50 centimetre cubed of 0.1 molar sodium hydroxide to the 50 centimetre cubed of ethanoic acid, it's now a neutral solution. So you've got a salt, sodium ethanoate solution. It is not a buffer. And you can pause this one because it sort of says the same, may help explain it in a slightly different way that you prefer. And looking at a graph, got the pH on the y-axis, the x-axis there, you've got the amount of sodium hydroxide added. And when you've added half of it, your pKa equals your pH of the solution, and you've got the buffer region on that more horizontal, it's certainly not horizontal region. So you start off with your weak acid, and the pH is rising as you're adding sodium hydroxide through that buffer solution, and then continues to rise until you're stopping adding the sodium hydroxide when it's fully reacted. And applications. So the human body has so many systems that are very acid-base sensitive, and so you need buffer solutions so that any change, any addition, small addition of an acid isn't going to affect whatever system is working. And so knowing the pKa values of proteins and their amino acids, looking at enzyme activity, it's useful to be able to understand buffers. And in analytical chemistry, if you want a fixed pH, you can make a buffer to fix a pH. Obviously, if you add a lot of an acid or a lot of an alkali to it, it will change. So how do you know what buffer solution you need? Look at its pKa. And here in the body, you've got human blood with a pH within 1% of 7.4. And you've got that reversible reaction, so your weak acid, can't really call it carbonic acid. But if the pH rises higher than 7.8 or falls below 6.8, it could be fatal. And if you add the same amount of acid, small amount of acid, the buffered blood stays the same at pH 7.4, but an unbuffered solution would reduce the pH by 70%, which is not good. So using buffer solutions when culturing different bacteria, as it says here, their waste products affect the pH. A couple of examples given, and another buffer in when you're investigating chloroplast reactions. And many thanks to Washington International School Team Science and the IB chemistry students.